So we come to the third aspect that we will discuss today, which is also doing current through small materials. It is the reduction of the transistor size. That's what we call Moore's law. So I have another question. If you take your iPhone and you take out the chip and you look at the smallest features in the chip, in the computer chip of your iPhone, does anybody know which dimension it is? Has anybody ever demolished a computer chip to look at the silicon? No, I have. 14 to 22 nanometers. So Moore's law tells you that the number of transistors is going up and up, it doubles every 18 months. If you take transistor size versus year, you go down with this line, and it means that we are already in the nanoscale, in the nanotechnology area, and we are approaching smaller and smaller features. Here we see the microprocessors and their transistor count versus the date. And so here is the introduction of the Pentium. I remember the transition from 286 to 386. But now, the Apple A10 chip, okay, it has 16 nanometer feature. And if you have a Samsung phone, it is 14 nanometers. So the feature size in your computer chip is 14 nanometers. So that's like the smallest features that have been made. So you can see that. So the top-down approach with lithography, it has reached the level of large molecules. Some molecules are that large. So here we also see the same law. So this is the number of transistors and the size in nanometers. Indeed, in 2020, we have a 10 nanometer scale according to Moore's law. Okay, we are maybe at 14, but it's close enough. But Moore's law continues. So we have to go smaller. We have to go smaller than 14 nanometers. That is what, otherwise we have no more new computers. This whole business with Moore's law, it has also stimulated people to look at molecules as electronic components. So this is already 88. Somebody suggested to take 2 rods of metal, of gold, to position molecules over them. In this case, with 30 nanometer was suggested, and then measure the electronic conduction through the molecules, which can maybe behave as a transistor or as a diode. Computing with molecules, it has been a very large research area. And here people actually have taken a break junction, positioned a molecule in between and measured the properties. So if you take a very, very thin thread of gold, a very thin wire, and you pull it until it breaks, and then you stop, then you can make a gap which is only a few nanometers wide. So in between you can position molecules, especially with chiral groups, and then you can measure the electronic properties of molecules. So people have done that also with metal complexes, with thiol groups, with SH groups. And here you see the break junction. So in between this little break here, there are molecules, and they can behave like a transistor. You can also approach this in a supramolecular way. So in this way, using molecules, electronic components, it has gotten a lot of research, a lot of attention. Whether the future really is in the right direction, I don't think so. It will be lithography. Currently, the features are 14 nanometers, but they use something like 175 nanometer wavelength of light. The latest development in lithography is of course, ASML, this company that makes the machines to make computer chips, they want to do lithography with 13.5 nanometer radiation. So they are able to make radiation with 13.5 nanometers. And with that, they do lithography to make the computer chips. And it seems, as far as I know, that Impria is a company that sells the material, the photoresist. So they use these kind of tin-oxo clusters to do the lithography with. So these clusters can absorb this radiation and then form a pattern because they react, and you can basically treat it to make very, very small patterns. This is the direction that things are going, but okay, I don't think that they have actually made a commercial chip yet with this technology, but they are maybe in the lab, but not as a product that you can buy.